Let's build a deep, rigorous intuition for embeddings and vectors, starting from the most basic mathematical ideas and connecting them all the way to modern AI systems. Even for a highly technical audience, it is worth revisiting fundamentals carefully, because embeddings are so ubiquitous that we often use them without fully unpacking what they mean. Let's start with vectors. A vector, in the most basic sense, is an ordered list of numbers. That's it. If I write something like 0.2 minus 1.7, 3.4, that is a three-dimensional vector. Formally, it is an element of a vector space, typically Rn. Each component is a real number, and together they define a point in an n-dimensional space. Vectors support operations. You can add them. You can scale them by a scalar. You can compute dot products. You can measure distances. You can project one vector onto another. These operations are not just mathematical curiosities. They define the geometry of the space. They determine how we measure similarity, difference, direction, and magnitude. In 2 or 3 dimensions, we can visualize vectors as arrows in space. But in machine learning, vectors often have hundreds, thousands, or even tens of thousands of dimensions. We cannot visualize these spaces directly, but the same algebraic rules apply. The geometry generalizes. Now let's shift to embeddings. An embedding is a mapping from some domain into a vector space. The domain could be words, sentences, images, users, products, nodes in a graph, molecules, or almost anything else. The embedding function assigns each object a vector. The key property is that this assignment is not arbitrary. It is constructed so that geometric relationships in the vector space reflect meaningful relationships in the original domain. The phrase reflect meaningful relationships is doing a lot of work here. If 2 objects are similar in some task-relevant sense, their vectors should be close. If they are different, their vectors should be farther apart. If there is some structured relation between objects, that relation might correspond to a direction or transformation in vector space. So embeddings are about representation. They are about taking something that is discrete, symbolic, or structurally complex and turning it into something continuous and algebraically manipulable. Why do we need this? Because neural networks operate on vectors. At their core, neural networks are compositions of linear transformations and nonlinearities. A linear transformation is matrix multiplication. Matrix multiplication takes vectors as input. So if we want to process words or images or users with neural networks, we need to represent them as vectors. Consider a very simple example, words in a vocabulary. Suppose we have 100,000 unique tokens. One naive way to represent each word is with a one-hot vector of length 100,000. Each word corresponds to a vector with a single 1 and the rest 0. This is technically a vector representation, and it preserves identity. But it has no structure. The distance between any 2 distinct one-hot vectors is the same. There is no notion that cat is closer to dog than to planet. The representation is discrete and orthogonal. An embedding improves on this by mapping each word to a dense vector of much lower dimension, say 512 or 1024. These vectors are learned from data. During training, the model adjusts the vectors so that words that occur in similar contexts end up with similar embeddings. The geometry begins to reflect statistical regularities in language. The important conceptual shift is that meaning becomes geometry. Instead of saying 2 words are related because a dictionary says so, we say they are related because their vectors are close under some metric, such as cosine similarity. Let's talk about similarity metrics. The most common ones are Euclidean distance and cosine similarity. Euclidean distance measures straight line distance between 2 points. Cosine similarity measures the angle between 2 vectors, effectively ignoring magnitude and focusing on direction. In high-dimensional embedding spaces, cosine similarity is often preferred because it is more stable and less sensitive to scale differences. When embeddings are normalized to unit length, cosine similarity reduces to the dot product. This is computationally efficient, which matters when comparing millions or billions of vectors in retrieval systems. Now, how are embeddings actually learned? In most practical systems, Embeddings are parameters of a neural network trained with gradient descent. Suppose we are training a language model to predict the next word in a sentence. The model begins with an embedding matrix that maps token IDs to vectors. When the model makes a prediction error, gradients flow backward and update not only the deeper layers but also the embedding matrix. Over many iterations, the embeddings evolve to support accurate prediction. What emerges is not explicitly programmed. No one writes down that dimension 37 should represent animalness or dimension 142 should represent plurality. Instead, these properties are distributed across dimensions. The embedding space self-organizes in a way that compresses the information necessary to minimize the training loss. It is useful to think of embeddings as coordinate systems for concepts. Each dimension is a basis direction in a high-dimensional space. The model learns a basis that is convenient for solving its task. Different tasks lead to different coordinate systems. There is no single true embedding space for language or images. There are many possible embeddings, each shaped by data and objectives. Let's examine what we mean by dimension in this context. A 1024-dimensional embedding does not mean there are 1024 human interpretable features. It means the representation lives in a 1024-dimensional vector space. The intrinsic dimensionality of the data may be much lower. But the model uses the available degrees of freedom to encode various interacting factors of variation. In high-dimensional spaces, certain counterintuitive phenomena occur. For example, most randomly chosen vectors are almost orthogonal. Distances tend to concentrate, meaning the difference between the nearest and farthest neighbor shrinks relative to absolute scale. This affects how we design similarity measures and indexing systems. It also influences how embeddings cluster. Clustering is a natural consequence of embedding geometry. If many objects share similar statistical patterns in training data, their vectors will receive similar gradient updates and drift toward similar regions of space. Over time, clusters corresponding to semantic categories can emerge. In word embeddings, animals cluster together, countries cluster together, and so on. Interestingly, relationships between clusters can also carry meaning. For example, the vector difference between king and queen may align with the difference between man and woman. This suggests that certain relationships are encoded as approximately linear directions. While this linearity is not perfect, it demonstrates that embeddings can capture relational structure, not just similarity. Now let's broaden the perspective beyond language. In recommendation systems, embeddings represent users and items. Suppose we have millions of users and products. Each user is mapped to a vector, and each product is mapped to a vector. The dot product between a user vector and an item vector might estimate the likelihood of interaction. During training, if a user clicks on an item, their vectors are adjusted to increase similarity. If they ignore an item, similarity may decrease. Over time, the embedding space organizes so that users with similar preferences cluster together, and items with similar audiences cluster together. The geometry encodes collaborative filtering structure. Importantly, this allows generalization. Even if a user has never seen a particular item, the system can estimate affinity based on geometric proximity. In computer vision, embeddings arise from deep convolutional networks or vision transformers. The final hidden layer before classification is often used as an image embedding. Images with similar content produce similar vectors. These embeddings can be used for image retrieval, clustering, or anomaly detection. Again, the geometry reflects task-relevant similarity. In speaker recognition, embeddings represent voice characteristics. Audio from the same speaker maps to nearby vectors. Audio from different speakers maps farther apart. Verification reduces to measuring distance in embedding space. Across domains, the pattern is the same. Embeddings are learned representations that transform raw input into vectors whose geometry is aligned with the task.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.